So while I was stumbling around McMaster-Carr, I noticed this Eyebolt section had an interesting note on it here. The note reads that the capacity for the Eyebolt's lifting capacity is for vertical only, but they can be used to lift angular loads, so like up to 45 degrees. So normally, you lift upwards, but you could lift up to 45 degrees, but you do need an eye bolt with a shoulder, and the lifting capacity is significantly below the rated capacity. And then they go to recommend a hoist ring as a solution if you want to be lifting at an angle. But I figured that we'd take this moment here to go through and do a FEA analysis on the liftingness and how close these are to breaking. So I'm going to come down here and I'm going to grab this quarter 20 bolt here with the shoulder. We will download this, and I want the 3D step no threads. And I choose the no threads version because if it had threads, then that would add a lot of geometry to our model, but it wouldn't help us all that much. So switch over to FreeCAD here, and I will come up with a new part, and I'm going to import the part that I just downloaded. And there we go. And now in order to do this simulation, I need two things. So first I need a face on the top that I can pull up from, and then I need a second face at a 45-degree angle that I can pull kind of to the side from. And I also need to get rid of this kind of bit down here where it would connect to a material. And I'm just getting rid of that to simplify the model, since it's not contribute anything other than nodes and complexity. So in order to start with this, I'm going to switch to part. And the reason I'm using part here instead of part design is because we're not really making any modifications to this model. We're just kind of editing it. And part's a lot better at editing things than part design. So I'm going to actually switch out of part and go over to Sketcher. And I'm going to make a new sketch, and this here, if you can't read it, says top. So I'm going to make a sketch on the top plane. And looks like McMaster has put their origin at the center of the eyebolt, which is perfectly fine for us. So then I'm going to get a couple of lines here. So these are going to be used to split the model. And then I'm going to give myself one helping line, construction line there. And then I'll use the symmetry tool to make these symmetrical around these two axes. And then I'm going to make all four of these lines equal. And I'm just going to dimension the distance length of one of the lines, and they just have to be long enough so that they cut through the whole model. And then I'm going to angularly dimension this dimension here. Let's see, angular 45 degrees. Alrighty, and then looks like we just have one more thing we need to dimension, and that is the width of our faces. And this isn't super important, just want it about right. So I'll say that that's about good. That's a 10. And for this one, we don't have to constrain this, but we can, and I shall. Alrighty, and we'll close that, and then I'm going to switch over to part and use the extrude. And because this here is not a closed profile. It's going to extrude a surface model, which is fine for us. So 10 meters forward symmetrically, let's apply that. It looks like that's thick enough. Alrighty, and see, we got an extra extrude here. Not quite sure what this is. We will delete that. Okay, and then I need to, let's see, I'll make myself a cube here, and I will transform the cube into approximately the right position. And the goal with this cube is just to Boolean subtract the thread section away. So let's see. There we go, and it's covering up all of the threads there. And the height is Y. So height, let's see, we'll add just a few onto that. Oops, looks like it's not that direction. Let's try the width. The width is the correct direction. We'll just make this a little bit shorter. Let's see, that's probably good there. And then I'm going to come over here and we'll select this in the cube, and I want to Boolean subtract, and then I shall select the extrude and the cut, and I want to Boolean fragments. Let's see. Maybe Boolean fragments wasn't quite the right choice. Let's undo that. Extrude and cut. It must be slice apart. And looks like that is sliced apart but in the wrong direction. So let's do cut and extrude sliced apart. Okay, that's looking better. So you see we've got these two faces here that we can select from. So I'm going to switch over to the FEM workbench. I think we are ready for that. And we need a new analysis block. And for a material, if we come back over here and let's take a look at the data sheet. Let's see, what does it say? Over here, product detail. Wants me to log in. Well, unfortunately, I don't have an account, but this here says that it is steel. So I believe we'll just go with steel generic. So let's pick a steel generic. Alrighty. And then come over here. So we need a fixed geometry constraint. I'm going to just constrain this whole bottom surface as fixed. And the reason I'm doing this is because the surface looks like this, and we have a force pulling down here from the threads, and that should be equal to or greater than the force that we're pulling up. And I think that we will find that. So let's come over here, back to our web browser, and if we look up the clamping force of a bolt, that's what you call like the force that it's coming or squeezing two things together with. And let's see. Bolt clamping force chart. Alrighty. So we have a 440. So we have a quarter 20. So if we look at this one, it says the clamping force is 500 pounds, which just happens to be the same force that this bolt is rated for, I believe. Yep, see right here, 500 pounds. So those two are the same. And let us switch back to FreeCAD. So 500 pounds is the clamping force, right? So we've got our eye thing, little skirt, 500 pounds pulling down, 500 pounds pulling up. This should always be in compression. At least for this particular setup, this should always be in compression. The 45 degrees is a little bit more complicated because you end up with extra compression on the left and then kind of tension on the right, and you'd have to compare this tension against your compression. But we can take a look and see if this particular situation here is occurring after we run the simulation and make a decision based on that. So now we have an analysis. We've got a material, fixed constraint. I need a force acting on a geometry. So we do 500 pounds. I do need a 500 pounds to newtons. So pounds to newtons here, and 500, oops, not 400, 500. We got 2224 newtons. So come back over here, 2224. Okay, and we need a direction, oops, and I need to add my faces. Looks like that direction is not quite correct. So I'm going to switch back over to Sketcher and make a new sketch on the top plane. And we'll just add in some lines that we can use for directions. So do the vertical line and then the 45-degree line. And I'll just make these two equal. And I grab myself an angle between this and 45 degrees. Alrighty. And then I will just give them a length to fully dimension them. Okay. And let's come back over here to our constraint force, and we will choose the upwards direction as the direction. And I believe that is all of the constraints. Switching back over to the FEM workbench. And then I will grab the mesh and we'll mesh it, and we'll see if it spits out something that looks about right. I am looking for approximately, let's see, that doesn't quite look correct. Let me see. So it appears that our slice has sliced all the way through our part, which I guess is what you would expect it to do. And let's see if we can grab the exploded state. So maybe this explode slice is not quite what we were looking for. So I'll switch back to part. It is possible we were looking for Boolean fragments in the other direction. So let's see. I will delete this exploded slice. Oops, looks like FreeCAD has crashed there. So I'll bring it back up, and unfortunately I did not save. So we will get the joy of running through this again. Alrighty, so we are back. We will import this body. Alright, switch over to sketching, sketch, top face, and do that, this, and let's see. I'll grab the angle tool and we can do 5 degrees here, 5 degrees. Between these two, we'll do 10. And then from this one to that one, we will do 45. Okay, make them all equal. And we'll call that good. And let's see, back to part. We will extrude, symmetric, okay. And let's grab a Boolean fragments on these two parts. Let's try Boolean fragments the other direction. So it looks like neither of those are what we were looking for. So let's try slice the compound. That one sounds promising. Oop, let's see. Looks like that's what we were looking for. And put my cube back in. And I recall it was the width that needs to be taller. And transform that. Move it down and over this way. Alrighty, and Boolean subtract the two. Okay, switch over to FEM. Grab ourselves an analysis block, a material, steel generic. Oops, steel generic. Alrighty, grab ourselves a support. Here, 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 and one more face. Alright, we need another sketch, so head over to Sketcher here on the top face, and I need two lines, one like this and one at 45 degrees, and grab those two, 45, okay, and let's head back to FEM. We'll grab a force on this face and this face, the direction being this face here, and that force does need a 20 to 24, okay, and then I believe all we need is a mesh, and if we did this correctly it should mesh the whole part. Alrighty, that looks good. Let's see, looking at the mesh, does look like we have a good enough number of triangles. Does appear to be approximately 4 across in the cross section there. So we should be good here, and we write this to a file and we run it. And this isn't a super crazy difficult simulation, so I expect it won't take too terribly long. And it looks like it's already done. Okay, so let's take a look at the results, and looks like exactly what you would expect. So let's take a look at the von Mises stress. And the von Mises stress is basically related to the amount of energy that a material is absorbing at a particular point. And each material has a maximum amount of energy it can absorb per particular point. So we can go and we can look up for steel what is the maximum that it can absorb. So steel, and then the property itself is called the yield strength. And let's see if we can find a yield strength. So this says that the yield strength is approximately 250 megapascals, and the ultimate strength is 400 to 550. And the yield strength is where your material goes from being stretchy, where it'll go back to its original shape, to being not stretchy. So it will be permanently deformed once you get into the ultimate tensile strength. So let's head back over here to FreeCAD, and for the yield strength, we can see that this max is far above the yield strength, but I believe if we look at the histogram here, 250 Most of these points are well below the yield strength. There are a few that are above it, so we do have to do some deeper investigation on this. So let's close the histogram here, and let's close this, and we will put in a pipeline, results pipeline, and I want a clip figure. We'll choose 250. So this will show us everything that's 250 and above for von Mises. And then I want to render it as a surface with edges, and we'll just show von Mises again. Okay, looks like didn't quite do that right. So let's come down here, do apply there. Alrighty. So we can already see that not much of this surface is yielding. I'll bring back our shape and I'll edit the appearance. Turn up the transparency here. Alrighty. So we can see that the parts that are yielding here are these two bits up here, which are probably caused by our forces acting on that point, so that's okay. And then these sections on the edge here don't protrude very deep into the model. They're probably just like tensile bending as this part stretches up, but they don't protrude all the way through this cross section. So even though these parts are yielding, it's still probably okay because the majority of it is not. And then similar thing here, not quite sure what's causing that. It's possible that this is compression. We can check that if we come back over here to the results. Yeah, and it looks like this part is in compression. So that's probably okay. You know, it will be permanently deformed, but it's only a very small section. So not a super big deal. Let's bring that back. And then, of course, down here we've got the two fillets that we noted earlier, I believe. And that's because these are stress concentrations. As the stress flows down here and it makes its way around the corner, it tends to build up in these corners. So those are okay. They don't protrude very far into the model. So should be acceptable. I would not consider this, you know, anywhere near yielding. I suppose that they're considering the maximum to probably be a component of the threads down here, and the threads, you know, having a maximum load of 500 pounds. So that would be my guess. Because after 500 pounds, you're no longer pulling the part down. I guess your little skirt bit is not in compression with the surface anymore. It would then be in tension, and then you would have, you know, force on the threads, and you know it's probably based on the threads because we're not seeing, you know, anywhere near enough deformation or stress to warrant this part breaking. But let's see. We'll copy these results so that I can go back and look at them later. And we will just make some small modifications to the force constraint here. So modifications I'm going to make is getting rid of those two faces and adding in the 45-degree angle faces. And then I'm going to bring back the sketch with the 45-degree angle and click the direction so that it's pointing at a 45. Okay. And we will run this. I expect that this one also doesn't take a crazy long amount of time. Alrighty, looks like it's done. So we'll come down here and take a look at the results. And let's see. Looks like this is doing about the right thing. If we come down here and we look at this, it does appear that this half over here is in tension. So it is possible that that would be a concern for us because we are assuming that this section here is in compression. But I think it's safe to say that we can ignore that since the majority of the stresses in the previous one acted up here. If we do see stresses kind of in this lower bit, maybe we'll go back and take a second swing at that bottom constraint there. But I expect that we don't need to. One thing I do note here is the maximum stress is drastically higher. It's about 3 times higher than it was before. And if we take a look at the histogram, we can see that now we've got a large amount of this material is above the 250 mark that we were using for yield. So there is still quite a bit of it that's not yielding, but this is a quite a bit. So we will have to investigate further, and I'm going to use the same investigation technique we used before. So I'm going to come over here to the results and make a pipeline. I'm going to give the pipeline a scalar, 250, and I'm going to use von Mises and surface with edges and von Mises again. Apply that. And I'm going to bring back our cuts so we can see where this is occurring. Okay, so we can see here we've got a similar set of stresses that are being caused by our condition on these faces. And then we've got the same kind of bending stresses here that are caused by this portion being in tension. And I would expect that this section down here is caused by this section being in compression because of bending. And then on top of that, it looks like we have an interesting section here where the vast majority of this material in the middle is yielding, and that is pretty scary. Looks like we do have the same fillets here, although they are larger, but that's okay. They don't extend too far into the model. My main concern is this main central section. It does appear to have yielded almost all the way through the part. So I would say that this part in this configuration has exhausted the majority of its strength, and this would be very close to yielding. So I guess this is probably the reason that they say that you should not use this if you were trying to do something at 45. I expect if this was 90 degrees, it would be even more pronounced, and it would probably be failing in 90. But it's also possible that this is kind of interesting, but my guess is this is just a little geometry feature that were taken into account. My guess is that their 500 pounds being greatly reduced is maybe based on the shear cross section of the bolt, because this is a threaded bolt, and threaded bolts are not designed for like a shear load. You risk kind of bending the threads and having the threads themselves yield if you put too much force on this, and as opposed to having it distributed across the entire cross section, you are having, or across the entire kind of volume of threads, you are concentrating approximately 50% of this force onto the cross section in shear. So that is a concern there, but it's kind of interesting. I hope you learned something about this. I suppose we can check and see if this face here is in tension. And my thoughts on how to do that are to come over here to the results. And let's see, I want to grab the Y displacement, and we'll take a look I believe the Y displacement is the vertical displacement. Um, let's see. It is possible that it is not the Y displacement. That doesn't quite look right. This looks better. Um, so this is the Z displacement, which it might not be the Z displacement either. Displacement magnitude. How about the X displacement? So maybe it is the Y displacement and it just kind of looks funky. But let's see. Down here, you can see that this part is pulling up. I guess the colors are not as useful as one would have hoped. But you can see if I zoom in here that this green section here is peeling away from the rest of this part. So it is possible that that section would be in tension, or I guess would not be pulled back by our surface here. So that would be an interesting second investigation into this part. We might look at that in a future video. But seeing as all of the stresses down here were pretty small, and most of the buildup was kind of in this midsection where you've got all of these connecting points. I feel that it's safe to say that this bottom section would not be at severe risk, even if all of these stresses were kind of flowing into this corner section. So I won't deep dive into that today. I figure this video is getting pretty long. I do think I do want to note that if you're using this cut, or I guess this slice feature here, it does appear that you end up with this kind of extra geometry inside of your model. So you can determine whether or not that is what you want. But I think for this, the meshing handles that okay, and it doesn't interfere with our abilities to get a proper mesh. But if you were doing this kind of technique to create faces that were selectable, you might want to not apply it to your model directly, and instead like link to your model and then apply it on your linked version, so that your changes don't get stuck in your model. But yeah, I think I'm gonna end it here. I hope you learned something. I found this quite interesting. So I will end it here, and I hope you have a nice day.